Welcome to the Naked Arcology. The term arcology was first defined by Paolo Soleri as cities which embody the fusion of architecture and ecology. The arcology concept proposes a highly integrated and compact three-dimensional urban form that is the opposite of urban sprawl. Since then, the arcology concept has been popularized through books, films, SimCity, as well as other media, and has evolved in popular culture to additionally mean self-contained, self-sustaining, and automated city structures that provide its citizens with a highly livable environment. Most visions of arcology are artistic and beautiful, but vague. They are long on conception, but short on pragmatic functional solutions that fulfill human needs. We have designed an arcology that bridges the gap between the fanciful and the practical. What we have done is an experiment in possibility. We have envisioned a city that has minimal environmental footprint yet is open, spacious, and very livable. Wraparound automation then animates and supports personal and social needs to provide an optimum lifestyle within a vibrant environment. In the Naked Arcology, we will bring this pie-in-the-sky concept down to earth. We will first give you an overview of the city and its environment. We will then strip down and expose the underlying components and functional elements, then show how these elements work in concert to deliver comprehensive services to the community. After a relatively stable level of human population across history, the world population started to steeply increase in the early 1800s and has been growing exponentially since then with no let-up in sight. At the same time, the movement of people from rural to urban areas has been increasing and unrelenting. Urban areas all over the world are taking the brunt, and while inner cities are growing taller to meet the demand, the surrounding countryside is paved over until large metropolitan areas merge in an endless sprawl. Let's take a look at a graphic representation of Tokyo's growth between 1960 and 2010. And here is an aerial view of Las Vegas as it grew between 1986 and 2012. And this is happening to cities globally. Let's now take a look at an example of urban sprawl. The San Fernando Valley used to be a cowboy's dream of sprawling farms and ranches behind the hills of Los Angeles. And here is San Fernando Valley now. A sprawl of low-level buildings, essentially boxes, stretching out as far as the eye can see. Here are the streets with the inevitable strip malls, fast food outlets, and advertising signs, which are reminiscent of so many places on the planet. And, of course, the traffic you need to drive through to get anywhere. So, what is the alternative to this lifestyle? Let's look at the San Fernando Valley again. It has a population of 1.77 million people. By building upwards instead of building outwards, San Fernando's population could be housed in 3.5 cities of the type proposed in this video. This would leave most of the valley green and available for natural range land, wildlife, and recreational use. And there are other benefits. As just stated, because of its small footprint, building a city arcology frees up the land around the city. And, since the city is self-sustaining, producing most of its own food and consumer goods, lands that would otherwise be used for farming and manufacturing are also freed up. Transportation also becomes more efficient. Going from one side of the city to the other takes minutes. Travel between cities is equally efficient with direct mass transportation. Additionally, since most items are produced locally within the city, traffic for delivery transport is reduced exponentially. Energy is drawn from local natural sources, plus the city's compact size reduces thermal loss, saving energy, and since the city is constructed in a compact, three-dimensional space, it could be efficiently designed like an engine, as a complete delivery and recycling system. All functional components could be automated and fully integrated so that every output has an input. The city could be optimized for livability. Automation could provide citizens full services at a high standard of living in an environment rich in exercise, recreational, and entertainment venues. And since the food is grown locally, it is always fresh, full-flavored, and healthy. So how does the density of this arcology compare to other cities? Here's a list of some of the world's most populated cities and some suburban areas. The density of arcology fits in between that of major global cities. The difference is that in arcology, most of the manufacturing and agriculture happens within the city, whereas current cities need vast amounts of land outside the city to support them. And here is the density comparison between the arcology and our San Fernando Valley example. So, let's take a look at a model of the arcology. This arcology is situated in a moderate climate on an ocean shore in a non-seismic zone. It provides its 500,000 residents with a comfortable lifestyle in a garden-like setting. This design is just one of many potential designs that can be adapted to various climates, topologies, and conditions to create effective and unique cities. The city at its longest extent is 4.8 miles in diameter. From the ground to the top of the structure is 3,000 feet, and it has a basement area 240 feet deep. The city itself is a unified structure housing most of the elements needed to supply the population. Since the city is on a seashore, water and energy can be provided locally. Water is taken from the ocean, desalinated, and pumped for storage in the city, while electricity is generated through tidal action, which is constant and reliable. Both of these systems can be built out of sight under the ground. Indoor fish tanks can provide the seafood, and ground fruit, vegetables, and spices can be grown indoors aquaponically. But tree fruit and grains would need to still be grown on outdoor farms. Equally, while farm animal parks for children would be nice in a city, you don't want livestock roaming around the city, so livestock would also be best raised outside the city. Also, large equipment would be impractical to build in the city, and would be best handled by factories that several arcologies share. These factories could also be built underground, leaving the foliage above in peace. Looking at the arcology from the side, it is composed of a basement area and a production and service area that contains the indoor farms, factories, kitchens, washing facilities, hospitals, etc. Then a horizontal distribution area, which is composed of multiple layers that handle product delivery and transportation, as well as water, electrical, and communications piping. At the top of the base structure are public entertainment and meeting areas. And the superstructure, while housing many of the residents, also contains infrastructure components as well as entertainment venues. Let's get a closer look. As you can see, while the city is densely populated, it is mostly covered by parks and wooded areas. The residential areas are all on the exterior or skin of the city, so every resident has a magnificent view. With 244,000 residential spaces, the city houses 500,000 people. The public areas are extensive with a variation of recreational, dining, and entertainment venues. Let's take a more focused look at the public areas. At the four crests of the city are cascading sets of garden terraces. A closer look shows the gardens, each uniquely designed, with a brook that cascades down the terraces. At each end of the terraces, there is a restaurant and patio. A combination of escalators and elevators move people among the terraces and different levels. The protrusions, that look like ship smokestacks, are sunlight shafts. Lenses at the top track the sun to concentrate and absorb maximum sunlight. Inside the shaft, mirrors deflect the light into multiple other shafts which distribute natural light to the interior throughout the section of the city. At night, robotic gardeners come out of their enclosures to trim and maintain the gardens. There are 4 large 1,600 by 1,000 foot parks, one located at each end of the superstructure. While our depiction is rather simple, parks these size would be lush with extensive foliage, lawns, and ponds. The jungle incline is heavily forested with pathways crisscrossing over a river rapid that flows down the incline. The rapids are used for rafting, and with 8 rapids in the city, different degrees of difficulty could be built into each rapid. At the bottom of the inclines, and adjacent to the central tower, are the central courtyards which provide meeting and lounging space. The courtyard is enclosed by a continuous building that spans across the 2 adjacent inclines. The building provides dining and lounging venues, as well as rafting facilities where clothes can be changed, equipment checked out, and escalators taken to the top of the rapid. A large tree-lined walkway with adjacent flower gardens allows for a leisurely walk between the courtyard and the entertainment canyons. The entertainment canyons are centers of social life. There are 4 sets of canyons in the city, and different canyons can serve different social crowds and purposes. Envision the canyons as meeting spaces with theaters, dance halls, game pavilions, skating rinks, dining facilities, and hair salons, as well as showrooms displaying all types of consumer products which could be selected and delivered to your home. Multiple stadiums for various sports, as well as concert halls, are embedded into the surface of the structure. They are accessed via multiple surface paths, as well as extensive hallways that connect from the entertainment canyons. These venues all have sliding roofs for inclement weather and are supported by kitchens that automatically cater the events. Most of the surface of the city is parkland. Multiple walking, running, and biking trails wind through the parkland. And at various points the parkland is dotted with sports fields, tennis courts, refreshment kiosks, as well as discrete restaurants. The city contains an internal boat dock for pleasure craft. The boats have separate entry and exit ways for efficient traffic flow. Inside the city is a large docking area to accommodate the ships. Adjacent to the docking area are automated facilities for cleaning and boat repair. The structure can also hold a large collection of ships in dry dock in vertical parking slots in the floors above. On the ocean side of the city is a large bathing beach, and behind the beach, the first 6 floors of the city are flanked with a continuous set of window banks. The windows allow natural light into a vast expanse of swimming pools. Citizens can enjoy a wide variety of water sports such as swimming and wave surfing, while children have access to wading pools. There are also multiple saunas, mud baths, and hot tubs blended into the facility. Overall, the city provides an extensive variety of environment for a vibrant social life. The city provides complete automation to service residents with a natural foliage-covered, peaceful environment. Let's explore the city's interior. The city's interior consists mostly of infrastructure components and lights out production facilities to service the residents at the city's surface. We'll describe the city from bottom to the top, so we will start with the basement. The basement is 3.4 by 3.4 miles in diameter and 240 feet deep. A transportation tube with a set of tracks, which connects the city to the outside world, runs through the basement. The tube contains several tracks that handle the traffic going in and out of the city. The transportation tube runs through the central tower of the city and delivers passengers to the city station. The tower is the main conduit for vertical transportation within the city and contains multiple elevator banks. There is a freight track that goes around the tower and stops at a freight depot. While the city recycles all of its components, there are still items that are sourced from the outside the city. The items are moved from the freight depot and distributed to elevators that bring the items to the appropriate supply warehouse in a set of factories located above the basement. At one end of the basement are 3 fish tank encasements, which are about a mile long each. Each encasement is subdivided into multiple fish tanks which contain environments that are conditioned specifically for the targeted fish population. The fish encasements are aligned with an indoor hydroponic garden located in the floors above, which we will cover later. 6 large water tanks store fresh water for the city. 4 of the tanks directly support the city's residential use, while 2 tanks support the city's factories. Sewage treatment also has a set of 6 tanks for waste processing. There are also 6 HVAC complexes to keep the city climate controlled, as well as 6 electrical storage areas that distribute energy to various substations throughout the city. The city pool facilities are embedded within the basement to allow for a spacious open area receiving natural light from the banks of windows above. Superimposed over the basement is the production and service level, which is 636 feet high, containing 53 floors. It contains an indoor hydroponic farm which is situated above the fish tanks. The farm grows multiple ground fruits and vegetables as well as spices. Next to the indoor garden is an aging complex. Here, food products such as cheese and wine are aged, and multiple other long-duration processes carried out. The raw food production complex creates basic food items, such as you would currently buy in the supermarket. These food items are then distributed to automated kitchens within the city for meal preparation and also to residents who want to do their own cooking. Residents can also create their own recipes, such as a new flavor of chili sauce or ice cream, and then submit to the custom food production complex. There, the item is prepared and shipped to your home. Other residents can try the new food item, and if enough people like it, the recipe can be promoted to the standard production complex. Attached to the food production complexes is a recycling facility. Since food waste is mostly treated through waste treatment systems, the purpose of this recycling plant is to sanitize and refresh food production factory vats, containers, tools, as well as delivery trays and other items used in the production and distribution of food products. At the other end of the factory complexes is the product production factory, where all consumable products such as televisions, phones, toasters, etc. are made, as well as some infrastructure components for the city. There is also a custom production factory where you can submit your CAD designs for new products and have them manufactured. To cap it off, there is a product recycling plant where all discarded consumer items are inspected, repaired, refurbished, or dismantled for parts automatically. Here is how these production units work together. The fish tank provides nutrients to the indoor farm, while the farm filters the water and sends it back to the fish tank in a regenerative system called aquaponics. The fruits, vegetables, and fish are harvested and moved to the food production factory for processing. Some of the food items are then placed in the aging area as part of the basic food production process. The aging area is used for long-term processes like aging cheese, wine, as well as pasteurizing, curing, pickling, and smoking food items. Products requiring chemical processing, such as fermenting and brewing, would be found here. Additionally, the various production compartments could grow foods such as mushrooms. When the processing is complete, the food products would be sent back to the food factory for completion and delivery. Both the food factory and the production factory are supplemented by external sources. The food factory imports food items that are impractical to grow locally, and the production factory equally receives components that are impractical to make locally. Also, the city itself is supplemented by capital goods items that are manufactured externally and placed into the infrastructure. The product factory and food factory then deliver their products directly to consumers, intermediary processing facilities such as kitchens, and to robotic systems that maintain the infrastructure. When components are used up, they are processed through the appropriate recycling process, which can range from cleaning to disassembly and decomposition, and then brought back into the production facilities for reuse. The city produces 90% of all items consumed in the city, and imports about 10% of products. To continue with the service level infrastructure, near the central tower are a pair of hospitals. These hospitals are for tests, health maintenance, acute emergencies, and operations. Convalescence would be best somewhere outside the city in a refreshing, natural setting. There are also redundant laundries where the residents' laundry items are cleaned. Each item has an electronic product label which tells the system which process to use to clean the item, and a label that identifies the owner so the refreshed item can be returned. The item is also inspected and the owner notified if a replacement is needed. Multiple sets of kitchens produce a vast variety of meals which are distributed to residents within minutes. And adjacent to each kitchen complex are dishwashing facilities where returned dishware from residents is sorted, washed, dried, and inspected before it's returned to the kitchens, where it is added to trays with napkins and cutlery ready for use for the next meal. Above the swimming pool is a multi-level gymnasium equipped with weight machines, aerobic rooms, basketball courts, squash and indoor tennis facilities, as well as full-size running tracks to keep the residents fit while they live in their automated lifestyle. And here are the contours of the internal boat harbor. And on the opposite side is the car distribution and storage complex. At the bottom of the complex, cars are picked up and dropped off. There are also automated cleaning and repair facilities and ample parking storage in the floors above. Above the service and support area are a series of distribution channels, or floors, which serve as the city's main horizontal arteries. The arteries bisect vertical shafts, which then deliver their payload to the target area. We will cover these distribution channels from the bottom to the top floors. The first set of floors are for hard good deliveries. These floors lie right above the production level and distribute products to consumers and intermediate facilities such as kitchens. They also carry products for consumers to the recycling centers for repair and disassembly, as well as transfer multiple other items between consumers and the various facilities. The second set of floors carry traffic for 4-passenger people mover pods. These transporters are accessed through elevators from the city's surface. From there, the passengers are whisked horizontally, vertically, and diagonally to their desired city destination using optimum pathways. The third set of floors carry piped liquids and gases. Fresh water, wastewater, hydraulic fluids, liquid food supplies for the kitchen, as well as HVAC and heat exchange ducts, plus other items that are distributed through the arteries. This set of floors is encased in an impermeable membrane in case of spillage. The top set of channel floors carry electrical, communications, and other cables. Above the distribution channels is the community's main social space. Here we separate the social space from the residential area which encircles it. The social space is 20 floors deep and is honeycombed with entertainment malls and office space further away from the malls. Access to the grounds above is by elevators, and there are small courtyards strategically placed near the elevators. Light shafts dot the parkland above and funnel natural light down to large foyers that connect the office spaces. Elevators also bring people down to the pods in the transportation area, from which they are whisked to their next destination. The upper floors of the social areas serve an additional function as they support systems from the forest and lawns above. These floors allow for sufficient soil to grow trees, a drainage system that recycles excess water back to the top, as well as a water system for the sprinklers. At the bottom of the ground support system is an impermeable shield encasement that prevents water spillage to the floors below and blocks root expansion. Above the common grounds area is the city's superstructure. At the points where the wings of the superstructure meet the tower are large air vents that allow wind to efficiently pass between the winged sections during the storm events. While the outside of the infrastructure is residential, the interior of the infrastructure contains some vital city components and entertainment venues. To get a better look at the interior, let's remove the cascading gardens on the top of the infrastructure. At the top of the tower is a small freshwater reservoir pool, and in the wings are larger water reservoirs. The top reservoir provides water to the floors above the lower reservoirs, which in turn provide water to the city below. The water is pumped from the basement and maintained at an appropriate level dynamically. The city contains a 3,000-foot world-class ski run, as well as water slides, skateboarding, and other downhill venues. The run starts near the top of the tower of each of the wings, turn back below the jungle incline, then wind between gaps of the production and service support level to the basement and finish at a set of tower elevator banks, which take the sports enthusiasts back to the top of the next run. Here's a cross-section of the downhill ski run, which actually contains several runs winding around each other to create unique and challenging skiing. At points, the runs meet in wide slalom slopes with chalet restaurants overlooking the slopes, and then the runs diverge again. Full automation is built in, so the depth of snow is regulated by snow dropping down from the ceiling as needed, and if the snow is too thick, it is melted by heaters under the floor and the water is allowed to run off. Wooded scenes are projected on the wall for that mountain atmosphere. Crash areas are coated with foam rubber to prevent injuries, while updated electric signs at regular intervals inform skiers of the situation ahead, and the robotic ski patrol is there to pick you up in case injuries occur. The skateboarding, water slides, and other downhill venues have similar challenging runs. Embedded in the various runs are areas for beginners and children. Refreshments are available at a variety of restaurants. The support area, running below the jungle incline, consists of a raft return to bring the rafts back to the top of the incline, an escalator to deliver the rafters back to the top of the next run, and a water return that continually pumps the water back to the top to keep the stream flowing. Robotic systems that maintain the forest are also embedded within this area, and an impermeable shield separates the jungle from the forest below. The cascading gardens have a similar support area which recycles the water, provides transportation between terraces with escalators, and houses robotic maintenance systems. The terrace support area also has specialty kitchens with attached dishwashing facilities that support the restaurants above, as well as an impermeable shield. As previously stated, all the housing is located on the exterior skin of the structure. The city houses a population of 500,000 people with an occupancy rate of 2.05 people per unit. There are a variety of unit sizes, but most units are in the studio to 2-bedroom range, since there are fewer large families in the post-agrarian world. Besides having a spectacular view, each unit has a large, fully automated living space and is physically positioned for privacy. Looking from above, we see the housing unit distribution across the city. All units are built on a slanted angle so they can get unobstructed views, and so that there is no direct physical view into any unit for maximum privacy. Let's take a look at a basic two-bedroom home. Each unit is sandwiched between two service support bays. The home includes the following: large balcony, living room, a den, dining room, kitchen, utility room, 2 bedrooms, and 2 baths. Also, there is a holodeck where media projections can be wrapped around for complete immersion. Additionally, the unit contains a large den and a utility room. At 2,500 square feet, the units are truly spacious, especially when compared to unit sizes in any major city in the world. Each floor is 12 feet high with an 8-foot high living space and a 4-foot ceiling space for support beams, piping, service support, and insulation. Taking a look at the environment around the unit, we see 3 units next to each other. A spacious hall runs along the units. The halls have elevators at regular intervals and skylight shafts that bring in natural light. Behind the hall is a resident support area. Transport cabs move people throughout the city and run every 10 floors within this area, so residents are never more than a short elevator ride from home. On alternate floors, there are other services for local communities, such as dog pooping areas, tended by poop scooping robots, as well as cat mazes where cats do their thing, and service robot parking for the various robots that keep the area clean and maintained. Other local support venues could also be built in this area, such as meeting and play rooms, as well as electrical, HVAC, and other environmental support systems. Now, let's look back at the 2-bedroom home where we will describe some automation features. While these homes have standard set of features found in modern homes, such as plumbing and heating, we will not cover those, but instead we'll cover the additional features that current homes don't have. One feature is a storm window. It unrolls to enclose and completely seal the home during storm events or upon occupants' request. If the storm window system ever malfunctions, the roll is retracted into the service tube that runs up and down the building and then is replaced by a new unit which is then put back into service. Another feature is the laundry chute, where all laundry, clothes, towels, bedspreads, etc., that are to be cleaned are placed into a chute and routed to a central automated laundry. Items are then sorted and laundered according to garment specifications. Laundry specifications and owners are tracked by an electronic tag embedded in each item. Items are also inspected for wear, and the owner is notified in case the item becomes defective. The owner can then choose to reorder a new replacement item. Discarded items are routed to recycling, where they are remilled into new material. Laundry can be deposited in both bathrooms. After cleaning, the laundry is returned to a universal closet where it is placed in the proper drawer or hung on the rack. The closet is an automated universal closet for all small household belongings and holds hanging clothes as well as linens and storage drawers. Newly ordered garments or linens are also automatically placed in the closet. The closet uses all 12 feet of the floor to provide maximum storage. The laundry return mechanism is encased in a service shaft which facilitates service and repair needs. The closet can be accessed from either the bathrooms or the main hallway. In the kitchen, prepared food is delivered from a choice of restaurants in enclosed trays. Up to 12 meals, if needed for parties, can be automatically stacked in the rack below the counter. And there is no need to wash dishes. All food trays, containers, pots, dishes, and utensils can be placed in a bin to be routed down a chute for the washing facility, where they are sorted, thoroughly cleaned, dried, and inspected before reuse. Both of these mechanisms are also encased in a support maintenance shaft. If you want to be the chef instead, food staples are delivered automatically, placed into the pantry or the refrigerator. This mechanism is also encased in a support shaft. The utility room contains the pickup and shipping point for most household items. The items are delivered on a cart through a delivery shaft, and the cart is released into the receiving area. Items that are being shipped out are placed on the rack and sent back into the delivery chute to be sorted, then sent to their delivery points. Meanwhile, large items, such as furniture, are robotically delivered through the home door. The cleaning rack contains a series of cleaning machines that work in tandem to automatically and efficiently clean the home. They are activated when everyone leaves the home or on request. When finished, they stack back up on the cleaning rack against an electric charger. The cleaning machines are attached to a set of tubes behind the charger. One tube sucks out the vacuum dirt, while other tubes resupply the machines with cleaning solutions, polish, fresheners, and other supplies needed for the next cleaning. Trash can be dumped into any 4 chutes located in the 2 bathrooms, the kitchen, and the utility room. The trash then is sent to a disposal area where it is sorted and routed to the appropriate recycling system for reprocessing. Taken together, these automated systems would free up time that people would normally use doing daily chores. Thanks to their new lifestyle, people could then focus on more creative pursuits. And when looked at structurally, each service bay can support 2 adjacent homes, since their service components do not overlap. There is also sufficient space for pipes and ducts for plumbing, electrical, and other environmental needs. Floating above the entertainment canyons, we view the canyon malls, ballparks, and concert halls embedded into the city's infrastructure. The wide expanse of canyons allows for multiple city quarters. Various quarters can be purposed for different civic needs, such as education and city management, while multiple other quarters can take on their own unique styles and atmospheres to provide various blends of entertainment for different social cliques. An image of the mall shows terraces populated with restaurant patios and brooks cascading down the terraces to ponds at the mall floor. Entries lead to the mall's interior, which is populated with theaters, dance halls, game rooms, and other attractions. The malls also connect the hallways that lead to the concert hall in the image. On the parkland above the canyons, walking and bicycle paths wind through the landscape and here provide access to the concert hall. With such a wide variety of activities in the malls, residents could find something to do based on their mood, desire for human interaction, and/or physical activity. As an example of the city's production facilities, let's take a look at the kitchen production complex. While city restaurants usually have their own individual automated kitchens to create their specialty cuisines, restaurant service that is provided to the home is created in large production kitchens. Here is a high-level view of an automated kitchen and its support systems. The entire kitchen assembly is composed of 3 floors. The middle floor is where the food production occurs. Supplies are delivered from the raw food production factory, either through piping for liquid and viscous food products, or a conveyor system for solid foods, which are then placed into separate food bins. The food components are then prepared according to the diner's preferences in the kitchen, and then go through several assembly processes until a complete meal is created and shipped to the diner. Above the kitchen area is supply storage and piping for the various liquid and viscous food components. Above the supply storage is a maintenance and repair shaft. The piping and storage components are bundled and built in assemblies which can be retracted into the maintenance and repair shaft. The assembly is then moved into the maintenance area for cleaning or repair. Meanwhile, a fresh assembly is reinstalled, filled, primed, and placed into production. The electrical and air conditioning ducts also run through the floor above, as does the water supply, which is essential for cooking. The floor below has maintenance and repair shafts through which cooking assemblies on the kitchen floor can be retracted and replaced with fresh assemblies. It also contains shafts through which used cookware is replaced. Additionally, there are ventilation systems, sensing networks, and multiple other components embedded in the three-floor complex that are not shown here. These kitchen complexes are stacked one on top of each other and are programmed for multiple cuisines. Some kitchens service ad hoc diner requests and create meals based on the recipes that diners submit. So let's take a more detailed look into the kitchen process. As stated, liquid and viscous food products are piped into the kitchen storage areas. So here we follow the solid foods as they are brought by conveyors. The food products approach the kitchen loading dock. The electronic label on the food containers are read, and some of the items are moved down shafts to the locations of their bins. The food items are then placed into individual ingredient holding bins, from which they are dispensed to the kitchen for food production. Each kitchen area specializes in specific food production items. Food items are made in large batches and then get subdivided into individual meals. From there, the basic completed food items are further processed, then moved to a fusion process where food items are merged to make your meal. This is where your mashed potatoes join the gravy and steak. Then the various garnishes are added to the meal. Meanwhile, drinks and juices go through a slightly different process. The assembled meals are then stacked on a meal buffer and ready for delivery to the diner. So let's pause here a second and take a look at the meal production process from a different perspective. The meal production is primed as the food items begin to be prepared before orders are placed into the system. An algorithm determines the food items that are to be prepared. The algorithm looks at historic data. If it's Wednesday, 1436 in mid-May, historical data shows that so many schnitzels will be needed. Or if it's St. Patrick's Day, a proportional increase of corned beef and cabbage will be needed. Environmental variables are also in the algorithm. When it's hot, proportionally more ice cream will be consumed. Public events will also affect the type and quantity of food that will be consumed. The algorithm also looks at the current consumption rates to dynamically increase or decrease the production. The meal items are matched to the order during the food production process. All systems within the arcology are redundant, so kitchens are duplexed in order to spread the production load efficiently. At the end of the process, the meals are sealed to maintain freshness and shipped to the diner. During low traffic periods, such as late at night, one of the kitchen pairs can be taken offline for maintenance to maintain a continually clean, functional, and reliable food preparation system. The city is basically a closed-loop system. That means that all inputs have their outputs in a continually regenerative process. Food and consumable items are produced in the city's factories. These items are then consumed by the city's residents, directly or through intermediary processes, or used in maintaining the infrastructure. Recycling then occurs at various levels. Services like dishwashing and laundering can be looked at as one level of recycling. Worn and broken items would move to decomposition or refurbishment processes and have a different level of recycling. And trash as well as waste have their own recycling process. The recycled items can be brought back into the production process or used within the infrastructure to create a complete closed-loop regenerating system. An automated supply chain management system runs production from end to end. Forecasting algorithms determine the timing and amount of each item from its inception, such as when and how many lettuce seeds to germinate or cell phone components to mold, and through all the intermediary production processes to meet consumption need and then back through recycling. All processes are tracked, storage buffers are placed strategically throughout the system to take up lag in various subsystems, and there is sufficient capacity to perpetually support demand. Supply chain management is currently used throughout the world to manage production, but it would be even more efficient in an arcology. Since all production would be in-house, it would eliminate the complexities and potential pitfalls of dependence on suppliers, distributors, customs, and long-distance transportation. All systems and components are fully redundant, similar to airplanes and spacecraft. If one component goes out or is down for maintenance, other analogous components maintain functionality and throughput. The system is engineered to maintain sufficient capacity when parts of the system are out of service. For the system at large to function efficiently, the individual system components need to be functional and responsive, and for that you need maintenance, component replacement, and repair. Depending on their functionality, system components basically come in two forms: roving and embedded. Roving machines, such as gardening, cleaning, and mover robots, have mobility and can move themselves to maintenance and repair shafts, or be towed if they are immobile. While system components that are embedded into the infrastructure, such as HVAC units, generators, and harnessed assemblies, have automated pathways through which they can be extracted and replaced, or access spaces through which they can be serviced, engineered into the infrastructure. Since all robotic systems need to function efficiently in a seamless environment, the infrastructure needs to be based on simplicity and common standards. In order to communicate within the work group and with hierarchical systems, each functioning component needs to have an IP address and communication functionality. Each functional component also needs to have an internal neural network so that problems with subcomponent can be noted in a log and transmitted to management systems for potential maintenance actions. All functional components and subcomponents also need to have an electronic barcode that can uniquely identify and track them in operations, repair, and the recycling process. Additionally, for ease of maintenance, items with potentially higher failure rates, like logic boards, need to be placed in a secure but easily accessible location on all robotic units, so they can be easily replaced. Universal and effective handles on all robotic units would allow other units to easily move and handle them during maintenance. For efficiency, fasteners would also need to be the same type across the system. Not that it's the ideal fastener, but let's take a look at the lowly screw as an example. There are currently multiple variations of screw heads on the market. If all variations were used, repair robots would constantly need to change out tools when repairing other robots. Proprietary systems would also add to the complexity, since individual companies have their own proprietary designs. To make the system efficient, simple generic fasteners with variations for different size components needs to be the standard across the system. Snap on, snap off. Make it simple. These simple standards are the building blocks for an efficient, synergetic system. Most people consider the possibility of robots fixing other robots to be an insane notion. But let's consider the automobile. Automobiles are currently built by robots with very little human intervention. The little human intervention that exists could also be automated to make automotive production entirely robotic. Automobiles are essentially functional machines which currently have neural diagnostic networks with automation features and soon will be self-driving. Essentially, automobiles are robots built by other robots. If robotic systems can build robots, why can't they disassemble them? As an example, let's go through a scenario where a robot breaks down on a product manufacturing line. First of all, since all robotic systems would constantly report errors that occur with its components, component problems would be resolved during maintenance. However, if a robot does break down, the first thing is to replace it with a functioning unit so that the line can continue production. The new unit positions itself in place, downloads its operational instructions, and the production line resumes. Depending on the problem, the broken robot moves or is towed to the repair station. The repair robot scans the broken robot's barcode to determine what type of robot it is and downloads the schematics and repair procedures for that particular type of machine. Diagnostics are run on the particular robot to determine the problem, and then the appropriate pre-programmed procedure is executed to make the repairs. The robot is tested and sent back into operations. Easy peasy. The production system we envision could make all types of products needed by the community, but it could not make all variations of products currently on the market. The latest celebrity-endorsed tennis shoe or cereal would most likely not be available. However, the latest and greatest foam gel generic tennis shoe in multiple designs and colors, as well as multiple cereal varieties, will. So where is the consumer's freedom of choice? Let's look at the lowly inkjet printer for answers. Inkjet printers have been around and pretty much perfected for the commercial market in the mid-1990s. Since that time, multiple companies have been producing essentially the same product while devoting vast engineering resources in producing constant new models designed with planned obsolescence, minor interface changes, and constant ink cartridge changes. So what do you want? The freedom of choice to choose between a vast array of inferior copycat products? Or the no-choice option of a superior product with optimal design that does not break down and has a large cartridge so you don't have to constantly go to the store and buy ink cartridges? One last item on robots and robotics. Robots do not need to look like humans or be sentient. While we are using humanoid-type characters to add humor to our points, robots do not need to look like humans or have personalities. They just need to be able to fulfill their functions and stay out of the way of humans. Furthermore, there is no need for sentient AI robotics. Most of the automated functions described in this video can be accomplished through standard programming methods and a low level of AI. Also, while this type of production facility could produce a wide variety of products and food choices, people could still feel boxed in into a standard fare. So, open input into an ad hoc production system is built into the environment. Here you can exercise your creativity by designing your own products through a CAD system, submit them to production to be created and shipped back to yourself. Or you could create a new recipe for chicken cacciatore, have the automated kitchen make it and send it to you. These new inventions can be posted for others to try, and if enough people like them, they could be incorporated into a standard production system. Here you have an opportunity to build a better mousetrap or become the next Betty Crocker. As you have seen, a densely populated city does not need to be stifling and claustrophobic. When properly engineered, a three-dimensional arcology not only frees up land around it so that humans can enjoy it, but also provide its inhabitants with all the needs of modern society in an open, garden-like environment and an atmosphere rich in educational, social, sporting, and recreational opportunities. The big question is, with all the automated luxuries, won't people take the route of least resistance and become lazy? The answer lies in all the small boxes spread out over all the suburbias of the earth. Are there lazy people living there? Of course there are. Most likely lazy people would also live in arcology. That's freedom. To paraphrase Forrest Gump, lazy is as lazy does. However, since the environment is rich in all types of opportunities and activities, most people would take advantage of them and flourish in this type of a city. We are a burgeoning population that are no longer hunter-gatherers and have evolved to a new level of technology where working on the farm, manufacturing, and even the service industry is being automated out of existence. We need new cities that respect the environment. Cities where we can harness the benefits of technological automation in an atmosphere of freedom, where humans can further develop their minds, bodies, and relationships. So, where would you like to live?